But modern AI has been fueled. In fact, modern AI has been reborn, regenesis, or reincarnation, thanks to massive amounts of data being collected over the net, but also the capability to process them, and that's HPC. So there's been 25 years of AI winter. So those of the lecturers here may remember things like the 5th generation project, or logic programming, or ICOG project we had, Prolog, stuff like that, which didn't quite work. And they were good, but didn't quite work. And so the hype curve and the downhill slope was so bad that resulted in 25 years of AI winter. But the neural networks, and especially deep neural networks, whose algorithms have been invented by people like Hinton, were there, but there was not enough compute power to basically make the expensive algorithms like backpropagation on deep networks be realistic or pragmatic. But fast forward 25 years, thanks to supercomputing, the computing power went up by 7 orders of magnitude, thus making the AI using deep learning practical. And started with AlexNet and Stanford Brain and Google Brain and so forth. But now it's AI is everywhere, and it's even increasingly becoming more sophisticated. And by sophistication, what the resulting sophistication is basically creating more demands for higher compute power, which I'll fast forward a bit. And so this is a chart showing what we were with around the AlexNet or DQN around 2013, 2014. But since then, there's been tremendous progress. And now with stuff like AlphaGo 0, we have experienced over, or again, we're able to cover something like AlexNet because there's an increase in 6 to 7 orders of magnitude increase in compute power. But now the deep learning has progressed over the past 5 years or so to demand 6 orders of magnitude increase yet again. So what was practical here is no longer practical. So how do we cope with that? Well, you have to cope with that using HPC. So, for those of you who aspire to work on AI, I'm sure some of you are, you chose the right discipline. There are plenty of people who can program frameworks using Python, but there aren't too many people who can program stuff underneath. And you could be one of those people who are the most valued by labs and companies. So when we say convergence of HPC and AI, well, there are 2 facets. One is acceleration of simulation using AI, meaning that is AI for HPC. So these include interpolation of extrapolation, log trajectory, molecular dynamics. So basically, you're trying to replace the first principle methods with more empirical methods, or augment or even to replace them. And so this has been met with substantial success. Was one of the Gordon Bell finalists, or finalists last year, as I'll tell you. So this is a very fruitful area. We have your HPC application domain, but you try to augment that using empirical methods. The other facet is the acceleration of AI. This is what I mentioned. AI was re-enabled by HPC, and require even higher compute power. There's insatiable demand for it. So, and there are many facets. But basically, we're trying to accelerate AI using HPC or HPC for AI. So at our center, and also with our partners, we're trying to work on both. So I'm sorry, this is in Japanese, but these are some of the application domains that are being investigated using augmenting simulation with AI, like pharmaceuticals, medicine, materials, climate, and manufacturing, as you can see in photos. So these are being worked on by us and also by our partners in the Fugaku project. And, it's not just us, in DOE, this Argonne. Argonne is looking at a whole bunch of stuff, trying to utilize artificial intelligence for driving science. So it's everywhere. One exemplar, this is a Gordon Bell Prize winner finalist last year. This was done by the Earthquake Center and also by us, because the PI has affiliation with us. So they're trying to basically do the seismic simulation with the earthquake and trying to shake the entire city. The whole city, the bedrock, the soil, and also the buildings. So, and then trying to forecast what would happen, what would be the credible evacuation route. But you have to have this holistic simulation, because just shaking a bedrock is enough, because there's soil structure, and then there are buildings. And they're using multiple AI methodologies. One is to predict the soil configuration using AI, because it's really not known what the soil looks like. So they sampled and they used AI, and also they used some techniques to predict how the soil distributions are. And also they're using AI to accelerate their solvers. So this is to, basically, they use AI to come up with the proper preconditioner, because these are, of course, iterative solvers. So they're greatly affected by the preconditioners. And by picking the right preconditioner, the AI picking the right preconditioner, they can, they get a 4 to 5, almost 5 to 6 times speed up over a traditional method. So these are some of the AI augmenting HPC. But on the other hand, we have HPC for AI. And the way we increase performance is to basically increase parallelism. That's the only way we know. Well, there are some other minor speedups that are available, but principally we try to speed up scientific applications by using massive parallelism, and AI is no exception, or deep learning neural networks are no exception. But there are 4 levels of parallelism. There's intra-chip parallelism. So the reason you may use GPU or like Fugaku CPU or some other dedicated architectures like TPU, Google's TPU, is you want the highest performance at the chip level. Then, of course, there are intra-chip parallelism to exploit that. But beyond the chip, of course, you try to connect the chips, and then you get parallelism across chips. And then those of you who know, this may sound basic to you. Just to reiterate, there are 3 levels of parallelism. There's a model parallelism, which in HPC term is domain decomposition. So you basically split the layers, right? And then you compute individual parts of the layers, and then combine them. And so that's the most basic level. I don't know why they call it model parallelism. It's really domain decomposition, but I don't know. And then there's data parallelism, in which you have the same network distributed all over, but you give it different data sets for training. And then every time you compute the gradient for back propagation, you try to aggregate the results, the gradient results that are computed across multiple nodes. And then there's hyperparameter search, in which you do the search for the optimal network configuration, learning rates, and so forth. So these 4 layers are independent, fortunately. So, deep learning is a massive HPC problem. So there are lots of ongoing research, including ours. So what we have done, just to give you a very accelerated view, is to tackle with the performance modeling of these, especially data parallelism. It's a little hard because, especially with some of the asynchrony possible with these trainings, you need a performance model with stochastic variables, but we've done that. This is still an empirical model, but allows us to do a fairly good prediction of the behaviors of training once given the network layer configuration. Build machines, Fugaku being one, but again, last year we built this ABCI, which is currently the fastest AI machine in Japan, at 4,000 GPUs. And also investigate whether Fugaku will be viable. Well, like I said, we've been able to add some acceleration features like convolution operators, like that. So Fugaku has, in order to, because about 80% of like CNN computations are basically convolutions. So being able to calculate low precision inner product is very important for acceleration, but also requires more bandwidth. So we have a very good chip, and also these parallelism, model parallelism, data parallelism require substantial network bandwidth and low latency. But like I told you, Fugaku, basically for HPC, we have that, and this will be applicable to deep learning as well. So done a comparison with existing chips, and you can read the numbers later, and also compare this across different machines like the Summit. And hopefully when we launch Fugaku, this will be the biggest and the fastest AI machine out there yet. And I'll skip over most of these, I'm sorry. And yeah. So I'll end this with a note. So there are many things that we're doing. But one thing we have been doing is trying to see how fast we can train the network, because that's after all what we want to do. And so training the ImageNet, is one of the very important benchmarks. Yeah. So how to train a million images with ResNet 50 at 75% accuracy has been a benchmark the last few years. And we tackled that with Tsubame 3, ABCI, and when Fugaku launches, we'll do this with Fugaku. But it's been a big battle between the giants. So Facebook started this one, I don't know, well, it started a long time ago, but Facebook, few years ago, used 512 GPUs and ran in 30 minutes. Preferred Networks did it in 1,000. Berkeley, this was done with nice landing, but with the Quarry machine. Tencent, they had their own GPU machine. And this is where it starts to get interesting. So then we built ABCI, which was a 4,000 GPU machine. And then Sony, of all companies, came out of the blue when they said, well, we'll do this. And they set the world record, 3.7 minutes. Unfortunately, this was responded to by Google a week later using their TPU. But then we are studying new algorithm, which is, for those of you who's doing deep learning training, just to give you a taste of it, we're doing, instead of doing stochastic gradient descent, we're partnering with Ryo Yokota at Tokyo Technology to try the quadratic descent or the natural descent algorithm using but sort of doing approximation of that using what's called a Kronecker factorization, which greatly reduces the amount of compute you need to do the matrix inverse computation of the Fisher matrix. But I'll skip the details. But which will allow us to greatly, increase the number of nodes. Because one thing is we need to parallelize, but the other is we need the stuff to converge. And when we start using very large batches, now the convergence goes to hell. So, but we've been able to, using the new algorithm called KFAC, and a very efficiently parallelized version of it, we've been able to increase the batch size to 130K, which is a world record. So this was published as CBPR recently. But the competition is very fierce because, like I said, Sony can train in 3.7 minutes using HPC. So now you can train these significant networks in couple of time. But Google responded a week later saying, oh no, we can train in 2.2 minutes. And then CBPR, which just happened. We said we can do 130,000 batch. Unfortunately, our training time couldn't beat Google, but we're working on it. But as we worked on it, Fujitsu came with a new paper, which said they train in 70, 74, 75 seconds with a batch size of 80,000, which doesn't quite match ours, but they're using a SGD. So I think this is the record size for SGD training. So as it is with HPC, deep learning HPC has become a fierce competition using big machines. And hopefully with Fugaku, we'll be able to increase the amount of processors used to 100,000 scale, and thus train in seconds instead of minutes. Okay, so that's about it. More, but I'm out of time. So again, this is sort of an outlook we have currently, but the last slide I'll show is, sorry, I'll skip all the research material. Yeah. Oops, yeah. What we're started to work on is to think about computing beyond. So we have conventional HPC, we're building this state-of-the-art new machine, which hopefully will be adopted everywhere. Also, the chips going to the cloud and so forth. HPC everywhere. Deep learning HPC. But we all know that Moore's Law is ending. Okay, so many of you, people who are my friends, hopefully career will not end to see this day. But those of you who are postdocs and students who will definitely see this, because you're much younger than we are. And so right now, we're seeing the end of the acceleration and that we have enjoyed for many years in silicon. Lithography shrinks. So we predict around 2025 to 2030, all of this may end. So, so it's like dinosaurs. We've been growing up, getting ever larger, more predatorial, so forth. But when Moore's Law ends, it'll be end of growth, as we know it. So of course we can't sit still, we don't, even dinosaurs turn into birds and they survive. Or maybe the mammals will become the new rulers. But whatever the case, we need to really think of the next generation of computing, whose performance growth will not come from increase in number of transistors. So what we've started on, and this will be sort of also a drive towards the next generation machine beyond Fugaku, and even beyond that, is to really think about post-Moore Cambrian, what we call the Cambrian era. So all of these new types of computing models, new devices, optics, quantum, neuromorphic, etc., and also conventional computing being accelerated, is what we really need to work on. Because otherwise, our machines will stop to accelerate. And thus we have very long stagnation. And people will not be buying new machines because if the growth stops, it's like cars, when they don't, because the market value doesn't increase in terms of safety and other things, people won't buy new ones. So this is what faces us in the next 10 years, 20 years, and that will be one of the main, along with other subject matters I discussed, will be one of the main topics that we cover by our center. Okay, with that, well, I hope you have a very productive week and also enjoy the Kobe nightlife. Thank you.